Hello everyone, I'm Siheng Chen, and this is a coworker with Yaoqing Yang, who is the audience here, and Elena Kovacevic and Christoph Lutzes, who is at another session. And the main question here is, so if we want to monitor the traffic distribution at the entire city, and we only have the budget to allocate limited cameras at a few intersections, where we should allocate those cameras, and to get as much information as we can. So initial idea is, can we borrow some techniques from classical sampling theory, which has a theoretical bound to show the information we can get. But however, the traffic data is not time series or images. The data structure is not regular, so we cannot directly borrow the techniques there. So the talk here is, we try to introduce and formulate a new signal processing framework called graph signal processing, which maps the data to a graph, and then we can generalize the classical sampling theory to graph sampling theory, and then we can use these techniques to handle this problem. So to build this connection, we first introduce this signal processing a little bit. So classical signal processing really focuses on these two types of data set, like images and time series. So both of them has a very irregular structure. Which you see here for the time series is a like line graph, and for images is a lattice graph. And each node has the same rule in this structure. But for main data, they actually associate with a complex structure. For example, the attributes in the online social networks and activities on neural networks. Their data associated with an irregular and complex structure. And then actually, we can build this framework and to extend the classical signal processing tools to graph signal processing, and to design tools like graph filtering, graph Fourier transform, or graph Wheeler transform to handle those data. And the difference between this framework and graph mining is, so graph mining really look at the graph structure and study the subgraph commit detection, this kind of problem. And graph signal processing really look at the interaction between the data and the structure. So let's see this relationship between graph signal processing and urban computing from this example. So here we construct, this is the Manhattan graph where the node is the intersection and the edges are the street segmentation. And this graph shows a natural skeleton of a city and map all types of urban data into this standardized and unified graph. And here I simulated one graph signal. Let's say this graph signal represents the distribution of pedestrians. And the height here shows the number of pedestrians. So higher means more pedestrian. And given the signal, we want to ask, where are those pedestrians? Where is crowded? So we may use some denoising techniques to denoise the signal and to preserve real information and filter out noises. So then we can use localization techniques to detect there's some event at the Central Park. Maybe people are playing Pokemon Go there. So the long-term goal for this framework is to use this graph signal processing techniques to analyze urban data and provide tools for urban planner to make decisions. So I finished the background. Let's go back to the monitoring problem. So the government put cameras at some selected intersections. And the real question is where we should put them to maximize information we get. So let's formulate this vehicle distribution as a graph signal, where nodes are intersections, and the signal sit on the intersection is the number of passing vehicles, which is a ground truth here, but we don't know about it. We only know about data from a few intersections. And the task is, can we recover them as much as we can to approximate the original data, the original ground truth. So basically, this is a sampling and recovery problem. We're sampling from the original data, get some samples, and we recover it. Actually, we know how to do this from classical sampling theory. So here's a continuous time series, and we take some samples, And Shannon and Nyquist told us if the original signal is band limited, then we can perfectly recover it. So band limited means that the signal energy concentrated in a low pass frequency band, which means that we can do the dimensionality reduction to push the energy into a low dimensional space and still preserve all the information. So actually, you can borrow this idea here and to ask if we can find this transformation from the passing vehicles to push the energy into a few final domain and do the transform and the energy still be preserved. So the answer is actually pretty straightforward. That's PCA. Let's do principal component analysis constructed from the historical data. Then we can push the energy into the first few components. And then we can do the sampling and recovery thing. So we're sampling from this unknown passing vehicles. And when we have some samples, then we do the recovery. The only thing we need to do is we need to recover those first few elements here. Then we can do this kind of inverse PCA. We can recover the original data. So this graph sampling theory thing really designs the sampling operator and the recovery operator to minimize the overall recovery error, which pushes the sampling operator to design samples that allocate those cameras to the intersections that having non-overlapping information and also give you important intersections. So the next question is, so real data is very noisy. Only PCA is not enough. PCA is not that stable or robust for noisy data. And also, we want to reduce the computation. So the idea is we want to group intersections to, based on the similar behavior, we'll group them into like a smaller block. So for example, here's a taxi pickup data on New York. I zoom in here, and you will see that for this region, the number of taxi pickups is large and kind of even distributed. And for data here, there are a few number of taxi pickups. So actually, you can group the data there. And remember, this is not a community detection problem because we consider both data and the graph structure here. So we need to adaptively explore the property of this data. Again, we can borrow ideas from signal processing. Like people do this piecewise constant approximation over and over again. For example, for time series or for those meshes data. And they build the techniques, for example, hard wavelets or these wash functions. So the main idea is to find a piecewise constant approximation to the original data. And for example, here, you assign one piece constant signal here to capture the variation. And so here, you capture the variation, this big jump here, and to filter out the noises at this constant. So we can use the similar techniques. We'll definitely search for an optimal piecewise constant signal to approximate the original signal and capturing the variation and filter out the noises. So this method is actually very similar to the wavelet packet tuning used in the image compression standard JPEG 2000. And for example, each time we compare a parent piece with its two children piece. So on the one hand, the parent piece gives a very concise representation. And on the other hand, the two children piece capture more variation. So we kind of do this optimization, do this trade-off. If we want to split, if the signal sit here is very smooth, then we don't need to split. But if there's lots of variations, for example, here's positive value here, negative value there, then we want this split. Use more pieces to represent the signal. So this is a pipeline for the entire system. And this is the learning stage. From the original historical data, we do this piecewise constant approximation first. Then when we have this piecewise constant approximation, we assign one super node to represent a few nodes. And then from those few super nodes here, we take samples. We design this sampling operator. Then in this real time phase, we collect data from a few intersections, and then group the data into the super node representation, and we use the recovery operator to recover all the distribution. And then we expand because it's a piecewise, it's a piece here, so the value theta here is a constant. So we just expand the data to the original data. And we use this guy, this approximation, to approximate the original data distribution here. So we validated this thing on a public open data set, the taxi pickups at New York. So we only look at the workday from Monday to Friday at the rush hour, and we use the data from 2014 for learning and 2015 for testing. So here's the 5 intersections we design. So actually, there are 2 intersections. They are adjacent here, but we need to collect them both, which means that, and this is around the Penn Station, which means that the Penn Station gives you lots of variation, lots of uncertainty. You need to allocate more sensors there to make sure you capture the variation, you capture the knowledge there. And here's the recovery comparison. This is June 16th, and this is a real distribution here. And the value bar shows the number of passing vehicles. And this is the recovered distribution. When we visualize them, they are very, very similar. And here's the daily recovery error. X-axis is the index of day, and y-axis is the mean average error, which means that the average error per intersection. So you see here is almost like 0.7 error per intersection. And there are some like outlier day, like Memorial Day and Labor Day. And we cannot do this prediction because the behavior is not like normal workday. Okay. So the summary is we propose this framework, graph signal processing for urban computing. And we propose 2 techniques, graph signal sampling and piecewise constant approximation. That's it. Thank you.